I'm Anil Kumar. Welcome to my series on trigonometry. We'll discuss sine functions, their transformations, and graph in this particular video. You can always contact me on the email address given here and check the latest uploads on our website globalmathinstitute.com. To begin with, we'll understand some characteristics of sine functions, take up transformation of sine functions. See how to graph sine functions and write equations from the graph. We'll look into domain range of a cycle of sine function and take up some examples which will help you practice for examination. As you see here, a sine graph is shown to you which is in red. The sine function starts at the axis, goes to the maximum, 0 minimum, 0 maximum, right? That is one particular cycle of sine function. We'll look into its transformation in this particular video. Now, a general equation of transformation is given by the equation f of x equals to a sine k x minus p plus q, where a is the parameter which gives rise to vertical stretch or compression. If it is negative, it does do reflection also on the x-axis. The parameter k is responsible for horizontal stretch and compression. It changes the period for the sinusoidal function. If k is negative, in that case, for a sine function, it becomes negative of sine x, so it gets reflected on the x-axis. P is for phase shift, translation horizontally by p units, and q is a vertical translation. Let's begin with the characteristics of the sine function itself. As you know, the sine function graph, which will consider one particular cycle for most of the cases. However, it is a periodic function where there is no restriction on its domain. So x belongs to real numbers is the domain of the function. As far as range is concerned, we have a maximum value of 1 and a minimum of -1, and that gives us the range between plus and -1, where the y values belong to the real numbers. Period of one cycle is 360 degrees. If you're working in radians, you can say 2 pi radians. The graph has odd symmetry, so we do have points. Sine of minus x is basically equals to minus sine x. That is what it means by odd symmetry, correct? Now, graph is concave down for the positive values and concave up for the negative values. So this portion, do you see it is concave down and the negative portion is concave up. That results into the local minimum, right? Maximum of 1 is at x equals to 4n plus 1 times 90 degrees, where n belongs to integers. So that is the maximum value of 1, right? So it repeats after every period of 360 degrees, the first one being at 90 degrees or pi by 2. The minimum is at -1, here it is, and the very first one is at 270 degrees, but in general we can write down this as 4n minus 1 times 90 degrees, where n belongs to integers. In all the graph and the transformation, we'll always consider the key points. These are the 5 key points which we are going to consider to begin with. Origin, right? So that is the starting of a sine function starts from the axis. So this line here is called the axis. Now, the wave which we call as the principal wave starts right from there at the origin. Then we get the maximum, 0, minimum, and 0. These five, these five are the critical points which we'll always consider for transformations. Perfect. Well, if you're working in radians, of course, 360 degrees is 2 pi, 180 degrees pi, 90 degrees pi by 2. Correct? Now let's take up this transformation where we'll consider the vertical stretch. So when we say vertical stretch, then y is equals to a times sine x. So this a, which also signifies the amplitude, gives you the vertical stretch. While in the transformation function, the general function g of x will be written as a sine k x minus p plus q. The parameter a affects the vertical stretch, compression, or reflection on the x-axis. So if a is greater than 1, that means there is a vertical stretch by a factor of a. For example, y equals to 5 sine x. So the amplitude will be 5 times 1, right? If a is less than 1, we're considering positive values. In that case, there will be a vertical compression. For example, y equals to half sine x. So the amplitude will become half. If a is negative, the graph is reflected on the x-axis combined with the stretch or compression, as in y equals to minus 0.5x. So if a is negative, what really happens is that the graph, which is shown here in red for sine x, right, it actually will now be reflected. So the points will be kind of like this. Do you see that part? Right? So that is how the wave will be. So let me sketch this in a different color. So that becomes the graph of sine of minus x. Or you can say it's minus sine x, right? So that will be the graph of minus sine x, right? So it gets reflected. Now here is an example, vertical stretch, compression and reflection. Consider the following set of sinusoidal functions. Y equals to a sine x for a equals to plus 2, 1 and minus half. So well, if it is 1, in that case there is no transformation taking place. It is the parent function y equals to sine x. When you have value of a as 2, that is to say, if the function is y equals to 2 sine x, then the vertical stretch is by a factor of 2 as shown here in the blue graph. So in that case, the amplitude, which was 1, now becomes 2. Clear? For y equals to minus half x, there is a reflection and the amplitude becomes half as shown in the green graph here. Now, as an exercise, I'd like you to pause the video and write down the key points on the transform function, right? That is to say, write down the image of these original points 0, 0, 90 degrees and 1, 180 degrees 0, 270 minus 1, and 360 0, right? So write the image points for the two functions rather, for the key points. Now we're going to consider the vertical translation. Vertical translation, as you can see, this is your standard parent function. The graph can move up by q units. In this case, it is 2 by 2 units. Or it could move down, for example here, minus 3, it will move down by 3 units, right? So it's a simple translation up and down, which is going to only change the range of the function. The other parameters, as period, amplitude, and domain, will remain the same. Correct? So this translation of up and down takes place. The parameter is q. If q is greater than 0, that means positive, then q units up will be the transformation. If q is negative, then the graph will be translated q units down. Example here is vertical translation of y equals to sine x plus q. So this parameter q gives you the vertical translation. Consider the following set of sinusoidal functions: y equals to sine q, sine x plus q, where q is 0, minus 3, and 2. So the three graphs shown reflects these different values of q. As you understand clearly, if q is positive, example 2, it will move up. If it is negative, the whole graph will move down. Perfect. Now, another important thing here is to list the characteristics which do not change because of the vertical translation. Now, this is a very common part in examinations. So, whenever you're looking into transformations, always see what gets affected and what doesn't, right? That should help you. Now, let's look into the horizontal stretch. Sine kx, the factor k provides us with the horizontal stretch or compression. It is also responsible for the time period, right? The relation is that k equals to 360 degrees over the time period, or when you're working in radians, it could be written as 2 pi by the time period p. So k directly affects the time period, so both are related. In the transformation function g of x equals to a sine k x minus p plus q, the parameter k affects the horizontal stretch or compression. If k is greater than 1, then the graph gets horizontally compressed by a factor of 1 over k. If k is between 0 to 1, horizontal stretch by a factor of 1 over k takes place, correct? If k is negative, we'll have a reflection on the x-axis. Since you know that sine of minus kx will be equals to minus sine of kx. Is that clear to you? Perfect. Now here is an example. Y equals to sine kx. K values are 1, 2, and half. For the three values, we have already drawn the graph here. The blue graph is for the default parent function y equals to sine x. Now if the value is 2, that means we'll have two sine waves within the interval 0 to 360, right? So there will be two sine waves. So like shown by the red curve. So the red graph is for sine 2x. When it is half, that means only half of the wave will fit in 0 to 360. So the period will be stretched to 720 if k value is half, as shown here. Now, what doesn't change? There are many things which change. Of course, the domain of a cycle will change, right? Phase, I mean, will change the time period directly, correct? The things which do not change are amplitude, maximum, minimum, and equation of axis, also the range. Now let's consider the phase shift. With that, you will understand individually the effect of each parameter on the transformation. So phase shift P basically moves the graph left or right. If P is positive, then the graph moves right as shown here. The example for you is y equals to sine x minus 90 degrees. So it moves right by 90 degrees, as you can see here, comparing the starting points or the maximum. If P is negative, that is less than 0, then horizontal translation is towards the left. Correct? As shown, you need to describe this particular function for a similar transformation. Well, here's an example, which is y equals to sine x minus 90. Graph is shown to you. In this case, for y equals to x minus sine x minus 90, the graph of sine x translates horizontally by 90 degrees to the right? So, as shown here in the figure. Now, you can pause the video and answer this question. You have this function y equals to sine of 2x plus 90 degrees. Can you tell me what transformation is taking place? Specifically, what is the time period and what is the phase shift? Well, to get the right answer, the strategy here is that you should always factor out the coefficient of x. So we'll factor out x first, and then we get x plus 45 degrees. Now that gives you the right transformation, right? So from here, we can say that the period for this particular function is, if you're working in degrees, as we have written 90 degrees, period will be, let me write p equals to 360 degrees divided by 2, or 180 degrees, right? So that is the k value, 2, right? That makes the period change. And the phase shift, lowercase p, is minus 45 degrees. That is to the left, 45. Do you understand? Right? So that is the transformation, kind of. This graph will be, I can sketch here, so it will move towards this side, left. Do you see that? So that is how the graph is going to be. Perfect. So basically, we'll move it to the left by 45 degrees. Clear? Now let's take up some questions which are, which you must be looking at in the examinations. Here is example 5, which says, explain why the following statements are true. 1. Graph of a, y equals to a sine minus kx is same as graph of y equals to minus a sine kx. And the second one is, describe the transformation and sketch the graph of f of x equals to 2 sine minus 3x. So that is related. So you can pause the video and answer this question. While the straightforward answer for this statement is that we know that sine of minus kx is minus a sine kx. And therefore, we have this statement. Because sine basically is an odd function, right? That is what it is. So remember, sine is an odd function. And therefore, sine of minus theta is equals to minus sine theta. Correct? Now let's look into the second part, which is describe the transformation and sketch the graph of y equals to 2 sine minus 3x. So we could rewrite this as minus 2 sine 3x. And that means that the graph will go downwards, correct? As shown here from the starting point. Now, minus 2 means reflection. Minus is for the reflection on the x-axis. 2 is the stretch factor. So instead of 1 and minus 1, the range now will be from minus 2 to 2. The maximum value, the amplitude, is going to be 2. So first is reflection along the x-axis. You have to describe from left to right, okay? So that minus signifies reflection on the x-axis. Then vertical stretch by a factor of 2, and 3 is horizontal compression by a factor of 1 over 3. Now these parameters will change many characteristics. 1. Amplitude will be now 2, right? And the period will be 360 divided by 3, which is 120 degrees. So these are the two major changes which takes place. Also, you will notice that the concavity changes, right? So the part of the graph which is negative is now concave up, and the part of the graph which is positive is concave down. Perfect. So we begin with a local maximum, a local minimum rather than maximum, right? That is a major change. So the graphs are already shown here. You will also notice that within a period of 0 to 360, right, which is for sine x, we have 3 waves. I should say 3 cycles, correct? So we have 3 cycles of sine 3x. And that is what that number 3 signifies, right? So if it is sine nx, there will be n number of cycles. Here's another very important question. Consider the function g of x equals to 3 sine half x plus 30 degrees minus 1. Describe the characteristics of a cycle of g of x. Write domain and range of one cycle of g of x. Describe the transformations of the function g of x. Sketch the graph showing all the transformations from the parent function, right? You can actually pause the video. You know all the concepts by now. So surely write down, begin with the transformations and then end with the graphs. So as far as the transformations are concerned, we could describe transformations right from left to right, correct? Move in this direction. So I'll begin with transformations, which I have mentioned here. Okay. So first we have a vertical stretch by a factor of 3, and then we have a horizontal stretch by a factor of 2, horizontal translation 30 degrees to the left, and a vertical translation of 1 unit down. Perfect. Now let's get back to the characteristics, which was part A for us. Now, from this equation, let's correlate. This minus 1 actually is the axis, and then 3 is the amplitude. To get the maximum, what do we do? To get the maximum, we add these two things and we get the maximum, right? So the maximum here is axis plus amplitude. Is that clear? Axis plus amplitude gives you maximum, and the minimum will be axis minus amplitude, correct? So that gives you a value of minus 4 as mentioned here. Axis plus amplitude or axis minus amplitude. Period. We get from the k value of half, so in this case it will be 360 degrees times 2, which is 720 degrees as mentioned here. Phase shift, you can directly read. Once you factor the coefficient of x, you can directly read. It is 30 to the left side, and therefore we have included minus sign. Now we're talking about domain and range of one cycle, correct? So sine functions are periodic functions. There are no restrictions on the domain. However, if you're talking about one cycle, in that case we can definitely write down the domain. Now the domain normally for a cycle will be from 0 to 360 degrees. Since the graph has moved 30 left, the domain is from minus 30 to 690, right? 720 minus 30 in this case, since the period was 720, correct? So let me rewrite this. This 690 you get from 720 minus 30 degrees, correct? That is how you get the upper limit for your domain. As far as range is concerned, we know from maximum to minimum is the range for this particular function. Now here is a general formula for domain of the function. It's very important that domain in general will be including the phase shift, and then it is from whatever the phase shift is. If it is minus or plus, that value of p. So phase shift to period plus phase shift, right? That is what the domain is going to be, correct? So in this case, phase shift was minus 30. And so minus 30 plus 360 gives you 330. That is how you get the domain. Clear? As far as the range is concerned, you have to go from the axis. If you subtract from the axis, you get the lower limit. And if you add amplitude to the axis, you get the upper limit. So that is the general formula given to you. Perfect. Now, let's look into the graph of this function. So what I've done here is sketch 4 different graphs, described transformations have been taken care of. So the function here is 3 times. So 3 times that 3 is the amplitude, right? And it gives you the vertical stretch. So the very first one is vertical stretch by a factor of 3, which is shown here in orange. The dotted line gives you the parent function sine x, right? So this is your sine x. And this is your transform function where stretch factor is 3. Now we will take care. So first you begin with the vertical stretch or vertical reflections. In this case, we have only vertical stretch. The second stage, look into the period. Now it is half of x. That means the horizontally stretched by a factor of, in this case, 2. So the period changes and becomes 720 degrees. 360 times 2 as explained earlier. So the graph in green indicates this particular transformation. And now we are going to incorporate the horizontal shift of minus 30. So in this case now phase shift is minus 30. So you can see this graph moves 30 units towards the left there also, correct? And therefore the cycle ends at 690, correct? 690 from minus 30, correct? So that is how you will incorporate the translation. And then 1 unit down, so that becomes the fourth step. You can actually combine 3 and 4. So fourth step is bringing it 1 unit down as shown here. So that is how you can actually sketch the graph using the transformations. Question number 7. This is also a very common question in most of the test papers. We need to now write the equation of the sinusoidal function from the graph. So here we have two graphs, correct? I'd like you to pause the video, write down the equation for these two functions. In this part, we're looking into sinusoidal functions. You may write for sine function as well as equivalent cosine function also to practice. Perfect. Now, how do we go about? Well, the key here is first to read the maximum minimum value, right? So this is the maximum value of 3. Also, we read the minimum value, which is in this case minus 1. Now, once you know maximum minimum values, you can find the axis, correct? So axis means Q. The value of Q will be maximum plus minimum divided by 2, correct? And then you can work out the amplitude A, which is maximum minus minimum divided by 2, correct? So you get these two values. So axis basically in this case will be 1 as shown here, correct? And the amplitude here is this difference, correct? Which is 2. So you have already got the value amplitude equals to 2 and the axis being at 1, right? Correct. Now we need to figure out what is the period, right? So for a sine wave, you can start from where the point touches the axis, right? So you have to look at the point where the graph is moving up from the axis, correct? So that is the starting point. So this point here is actually pi by 12 to the right. So we know that lower p is pi by 12, right? That is the phase shift. Now, from here, this is your half wave, right? So we have 1 pi by 12, 2 pi by 12, 3 pi by 12, 4 pi by 12, right? So we have a period which is equals to 4 pi by 12 times 2, right? Because this is half wave and full wave will be twice. So we have a period of, you can simplify this, that goes 8 and then, 4, 1 over 3, 2 pi over 3. So that becomes the P, the period. And from here you can find K, which is 2 pi by P. And so you can get this period of 3, right? So 2 pi by P of 2 pi by 3 will give you the K value of 3. So that is how you can get the equation of the function, correct? Likewise, you can also work with the other wave, correct? So read the maximum minimum values, then you find the axis. So in this case, it is 50 and this is 20, correct? Add them 70, 35 will be the axis. So you get the axis. But this is only half the wave, right? So what you have to do here is, because from minimum to maximum, it is half the wave, it has come down and give you the full wave. But anyway, you can read what is the period. This is half the period, okay? So 100 minus 40 is 60. So basically, period will be 60 times 2, which is 120. And then do put all the calculations to get your answer. Perfect. Phase shift. You have to look for sine wave from this particular point, correct? So that is how you should be looking at the phase shift. Now here is the solution for both these functions which we have discussed at length. So as I was saying, you have to read the value of maximum, which in this case is 3, minimum is minus 1. We are writing capital M and lowercase m for maximum minimum. X's will be add them up and divide by 2, so we get the value of this axis is 1, and this is the value for Q. For amplitude, difference of these two divided by 2, amplitude is always positive, and that gives you the value 2. Period, as we worked out, 8 pi by 12, which is 2 pi by 3. So the phase shift is this distance, which is pi by 12, and the value of k was 2 pi by p, which is 2 pi by 2 pi over 3, which gives you 3. And so you get your function, which is y equals to 2 sine 3 x minus pi by 12 plus 1. Correct? So that is how you can write down the equation from the graph. Here is the last example right there. Again, we are performing the same operations, reading the minimum and the maximum value, which is 50 and 20. Excesses, add them, divide by 2, getting 35. Amplitude difference divided by 2, you get 15. Period is multiply the 60 by 2 to get 120. Phase shift is the point where this point is. So you can read this point midway between 60 and 80, which is 70, and that gives you the all the parameters. The value of k can be calculated as 360 divided by p, which is 3 in this case, and therefore you get your function right there. I hope this helps you to understand how do we write equation from the given graph. Clear? So these are very simple steps to follow. Just follow them and get the result. With that, we come to an end of our video on understanding the characteristics of sine functions, sketching their graph, explaining transformations, and writing equation from the graph itself. We also looked into the domain of a cycle and how the range can be worked out from the transformation formula itself, right? I hope that makes sense. Feel free to write your comments, share your views, and if you want to learn from me, you can always write to me on the given email address. Thanks for your time and all the best.